All right, so finishing up 8.3 today. We left off with this example yesterday. Did you all get to an answer, hopefully, for your little bit of homework there? So they state that we're going to estimate the true mean amount of NOx emitted by all light-duty engines of this type at a 95% confidence level. If the conditions are met, we should use a one-sample T interval to estimate mu. The data does come from a random sample, so the random conditions met, 10% conditions met, we can assume that there are at least 400 light-duty engines. There's probably way more than that. There definitely is. So definitely we can assume that. And we don't know if the population distribution of it is normal, but because the sample size is large, n is equal to 40, which is bigger than 30, we could be safe using a t distribution. So from the information given, we're given the sample mean and the sample standard deviation. To find our critical value, we use the t distribution with 39 degrees of freedom. You always subtract one from the sample size to get your degrees of freedom. There's not a row, of course, in the table that corresponds to that, so they're gonna get a slightly different answer here. Just saying. Okay, but it should roughly be close to what we have. So we plug into our formula, and we get our interval. Yours, like I said, yours will be a little different. That's okay. Okay, don't necessarily change your answer. They used the table, which they had to overestimate the degrees of freedom a little bit because 39 was not on that table. Your calculator gives you an even better estimate because you are able to do 39 degrees of freedom. That's another reason I don't like the tables. Okay, so your answer will be roughly similar to that. Is it roughly close to that? Then you can go with that as your answer. Okay. So to conclude, we're 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. Okay. I think I worded it yesterday. I was able to go through and finish this example with my third block, and I think that we worded it as a little different. We said that we're 95% confident that the interval from 1.1599 to 1.3751 captures the true mean level of NOx, which I put grams per mile then right there in parentheses, emitted by this type of light-duty engine. It is important to put the units in there. You can also put the units, they put it after the interval, but you could also put them on the numbers too, and that would be accepted as well. You're just writing it twice then, but that would be accepted. This sentence stem is just a sentence stem on how to write it, interpret it in context. It's not the end all and be all. It's not the only way you could write it. Okay. In fact, every time I write one of these in this sentence stem, it kind of irks me a little, I guess, because I know in college I wrote them a little bit different, but both were accepted. So either way. All right, so today we're going to look at choosing a sample size. Again, we're wanting to have a sample size to give us a particular margin of error. Okay, we want to be within a certain margin of error, just like we did yesterday with proportions at the beginning of class. We finished up 8.2 yesterday, just a little bit there at the beginning. It's the same idea, but now with means. Okay, so if we want to be within a desired margin of error when estimating a mean, in the same way we did when estimating a proportion. So to determine the sample size that will yield a level C confidence interval for a population mean with a specified margin of error, ME, we need to get a reasonable value for the population standard deviation sigma from an earlier or pilot study and find that critical Z value from the normal curve. Okay, this is if we happen to know what the population standard deviation is. We can use Z star times sigma over the square root of n. But again, we don't always know that. In fact, a lot of times we don't know. If we don't know the mean, we don't know the population standard deviation either, for that matter. So that could potentially change. So when researchers would like to estimate the mean cholesterol level, mu, of a particular variety of monkey that is often used in lab experiments, they would like to estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. A previous study involved this variety of monkeys suggests that the standard deviation of the cholesterol level is about 5 milligrams per deciliter. So obtaining the monkeys is time consuming and expensive, so researchers want to know the minimum number of monkeys that they will need to generate a satisfactory estimate. Okay. So for a 95% confidence, you find your Z star, that would be 1.96, inverse norm for that. Okay, again, we have an estimate for the population standard deviation that we can go off of. Since we know the population standard deviation, we can use Z. We can use the standard norm. We can use inverse norm, in other words. Okay, we will use that sigma 5 as our best guess for that standard deviation. And we set the expression for the margin of error to be at most 1 and solve for n. So 1.96 times 5 divided by the square root of n is less than or equal to 1. What they did right here is they multiplied both sides by the square root of n. And when they do that, the square root of n's cancel out there. And you get 1.96 times 5. They left it over 1 because there's nothing there anymore, but you could just even write it like that without the 1 in the denominator. And 1 times square root of n is just square root of n. And now they square both sides. So what they did right there in between is they squared whatever 1.96 times 5 is. They squared the square root of n, so that's how they're just going to get n right there. So n needs to be bigger than 96.04. It's kind of weird. That's what that example we did yesterday. That's that value we got for that example yesterday. That's really random.
That's a working, right?
That's super weird though, to get the same exact number, but whatever. So what we're going to need for our sample size then, since n needs to be greater than 96.04, we're going to need 97 monkeys. So because 96 monkeys would give a slightly larger margin of error than desired, the researchers would need 97 monkeys to estimate that the cholesterol levels to their satisfaction. Okay. Are y'all good with that? It's still the margin of error whether we know the population standard deviation or not, the margin of error is still the right-hand side of these two formulas. It's the part you're adding and subtracting from your point estimate. Okay, it's that part that you're adding or subtracting from that point estimate. This right-hand side of the confidence interval formulas, that is the margin of error. If we know the population standard deviation or have a guess for it, like we did here, we had a guess of 5. In the example, we can use the top one. That doesn't happen very often though. More often than not, we have to use the bottom one. This is what we did yesterday to find confidence intervals, because most of the time you're not going to know the population standard deviation. Okay? Only one person in my other class got that, John, about where I said, pity the fool that don't know their population standard deviation.
Who was it?
The reference.
Who was it?
Bo Fleming.
Really? Wow. Okay.
So,
Started generation.
nobody else knew it. Now, after the fact, then they realized it.
Yeah.
That they had to be reminded. That doesn't count. All right. Got just a little more. Almost done. Well, I guess we are done. So if we don't know but if we do happen to not know the population standard deviation, then we can use the bottom one and estimate a sample size. It just depends on what you're given. Okay? Questions about that? I thought there was another example, but I guess not. Okay, so we're going to work on a few problems with this.